So no actual new theory today. Basically, I just want to look at some past HSC questions. Just again, so we can get a feel for what's the level of difficulty they might go to. So I'll start off with an extension 1 question. So these are typical sort of one from back in 2007. So Mr. and Mrs. Roberts are going to the theatre. Lovely. With their 4 children. They're randomly allocated 6 seats to sit in. We want to know the probability that the 4 children are allocated allocated seats next to each other. Okay. So there's the probability, 3 factorial, 4 factorial on 6 factorial. So what's the logic behind that? Well, bottom of the fraction, no restrictions. So 6 people sitting in a row, 6 factorial. Top of the fraction, okay. The 4 children want to sit next to each other, so we arrange them first. So that's where the 4 factorial comes from. And now we're going to say, right, you've organised how you want to sit, so there's going to be yourself and the 2 parents, Mr. and Mrs. Roberts, so 3 people all up. We're then going to arrange, so that's where the 3 factorial comes into it. And that works out to be 1 in 5. So that's, I guess, a typical sort of extension 1 question. As I mentioned to you, the extension 2, whilst it's no longer in the current extension 2 course, loves to ask, or I should say used to love to ask, quite interesting questions. So I thought, let's have some fun and have a look at some of those. So a bag contains 12 red marbles, 12 yellow marbles. We're going to draw 6 out without putting them back. So probability that exactly 3 of those selected marbles are red. Okay. So it's obviously if it's, I'm just pulling marbles out. I don't care the order. I'm just getting 3 marbles out of the bag. So it's a combination rather than a permutation. I'm thinking of it as. So the bottom of the fraction 24C6, because there's just basically 24 marbles in the bag. I'm going to get 6 of them, but I want 3 of them to be red. So from the 12 red, I'm going to get 3, which therefore means that from the 12 yellow, I'm also going to get 3. So 12C3 times 12C3. So to 2 decimal places, which is what they've asked for, that's 0.36. Okay. Hence or otherwise, calculate the probability that more than 3 of the selected marbles are red. So I guess the first part, really I guess I'd call that, say, extension 1. It's, you could have that extension 1. This second part is where you really have to do some thinking. So probability that more than 3 of the selected marbles are red. So more than 3. So that means 4 of them are red, 5 of them are red, 6 of them are red. Okay. So all right, I could just simply add all that up on the top. So 4 red, 12C4, 4 from the red, times 12C2, 2 there, 4 from the yellow, plus 12C5, 5 from the red, 1 from the yellow, 12C1, and then all of them from the red, so 12C6. I suppose I don't really have to write 12C0, I mean that's just equal to 1 anyway. And that works out to be 0.32. But what I thought was interesting about this problem is that it said hence or otherwise. That's otherwise what I just did really. I haven't used part I. So there must have been a way of using part I. So here's how you could use part I. Probability of greater than 3 red. Well, if I use the complementary idea, I could say, well, that's 1 minus the probability that 3 are red, but also minus the probability of less than 3 red. You're probably thinking, why on earth didn't he just say less than or equal to? You see, the probability that less than 3 red would be the same as the probability of greater than 3 yellow. Because if you've got less than 3 red, you must have more than 3 yellow. But it's equally likely. Remember, there were 6 red and there were 6 yellow. So probability of more than 3 yellow would actually be the same as a probability of more than 3 red. So I now could rewrite my probability and say, well, hang on, 2 lots of probability of 3 red is 1 minus the probability of 3 red. And we've already worked out what the probability of 3 red is. So I get a half of 1 minus the probability of 3 red, and we get the same answer as 0.32. Different way of thinking about it, coming up with the same answer. So I thought that was quite an interesting question, that one. 2006. I think what made this one hard was basically getting your head around the rules of the game and making sure, right? So chess, we can have a home team and away team, and there's 4 chess boards being played. On every board, probability the home team wins 0.2, probability you draw 0.6, and home team loses a 0.2. So equal chance of winning and losing there. They then go and record the outcomes by simply listing W for a win, D for a draw, and so on. So for example, home team wins on board, that should be board 1, shouldn't it? Yeah, so home team wins on board 1, draws on board 2, loses on board 3, draws on board 4, then you write it as win WDLD. So that's how we record the score of that game. So how many different recordings are possible? Just a basic counting idea really, because on the first board there's 3 different results. I'm not worried about the probability of them at this stage, it's just how many different recordings could we make. A second board there would be 3, the third board there would be 3, the fourth board would be 3, so 3 to the power of 4, which is 81. Okay, now they're interested in the probability. So what would the probability of that result, win, draw, loss, draw, be? Well, let's sub in the probabilities. Probability of the win was 0.2, the draw was 0.6, the loss was 0.2, and another draw 0.6, and we get 0.144. And so far, so good. Now, you get 1 point for a win, half a point for a draw, and no points for a loss. So what's the probability that the home team will score more points than the away team? First thing I'm going to do is calculate the probability of them getting the same number of points. Now, how could they get the same number of points? Well, all 4 games could be a draw, and then they would end up with the same number of points. So that would be 0.6 times 0.6 times 0.6 times 0.6. We get 0.1296. How else could we get the same? 2 wins, 2 losses. Remember, the probability of win was the same as probability of a loss. So 2 wins, 2 losses. 0.2 squared times 0.2 squared. But you'll notice I've multiplied it by 4 factorial and 2 factorial, 2 factorial. Because it might go win, win, loss, loss. But it might go win, loss, win, loss. It might go loss, loss, win, win. So it's like saying, how many ways can I arrange the letters W, W, L and L? Well, that's the same as our word questions. So it'd be 4 factorial divided by the repetition. And each one of those would have the probability of 0.2 squared times 0.2 squared. So we get 0.0096. Okay. 1 win, 1 loss, 2 draws. That would get the same amount of points for both teams. So same idea. How many ways could I arrange win, loss, so WLDD? So 4 factorial over 2 factorial. 0.1728. Is there any other way we could get the same number of points? I think that's it. Okay, so add them all up, and there's a 0.312 chance that we get the same number of points. Right, so therefore, there's a probability of them being an unequal number of points must be 1 minus that. Now that unequal means some situations the home team will have more points than the away team, some the away team will have more than the home team. But remember, the win for an away team and a home team was equally likely. So therefore, logically, half of those would be when home team's ahead, half of those will be when the away team's ahead. And so we get 0.344. Quite a challenging little question there, the last bit. Have a look at this one. We've got a pack of 9 cards, numbered 1 through 9. We're going to draw 3 cards out at random and just going to put them down on the table, left to right. So if you like, it's like we're creating a 3-digit number. Probability that number we create exceeds 400. Okay. Well, if it's greater than 400, it's simply 6 and 9. Because it's all to do with the first card that I pull out. And as long as it's 4 or more, I know that the number that I end up putting down will end up being greater than 400. So really, the question could have simply said, what's the probability of the first number being bigger than 4? Okay. What's the probability that the digits are drawn in descending order? Doesn't necessarily mean consecutively, so you might go 9, 5, 1, but those numbers are still going in descending order. Well, probability, well, if there's no restrictions, it would simply be 3 factorial ways of arranging 3 digits. Okay. So there's 6 different ways. If I pull those 3 cards out, there's 6 different ways I could put them down. No matter how I put them down, only one of those will be in descending order. Therefore, the probability is 1 in 6. You could waste a lot of time there by working out, oh, what are all the different ways I could work out descending order? The key to this one was realising that it doesn't matter the 3 cards that I pull out. Regardless of the 3 cards that I pull out, only one out of all the possible arrangements of those 3 cards, they'll be in descending order. So there's a 1 in 6 chance. All right, so that's that. There's just a couple of questions from past HSCs. You can see the extension 2 ones, a little bit more thinking involved there, certainly above the level, I guess, of what we're seeing. Well, mind you, some of the challenges in the textbook aren't too bad. They got some good thinking in there.